working on, the circuit we're working on. And we did our computations, and hopefully y'all wrote them down, right? What we got here? Back in I don't see that. I don't think it's got right. That's right. So what did we get for what did we get for VB? What did we calculate? 1.75, and we measured 1.7 something, right? So we calculated for VE, we calculated 1.05, and we measured about that, right? And IE we calculated to be 477 microamps. And we didn't measure that because we computed it from a measurement, you know. And then DC we calculated to be around 6.6 volts, wasn't it? 6.8. We measured 6.6. Okay, and then 6.6, yeah, 6.7. And VCE we calculated to be what? 5.7. It measured 5.7. 5.1. Okay. So that was really neat in that we did our math, and then we went in and made our measurements, and we came up and got that right. But here's our actual circuit here that we got constructed. Now ours is a little different in that we can't get 1 volt peak to peak out of our function generator. So what I've done is I've come in here and replaced this with a potentiometer, a 10K pod. So we got rid of this, and then we got a 10K pod in here. So I'm just going to come over and scribble it right in here. And then we're bringing ours in right there. And then what we can do, and then whatever we get here, I don't know what we get out of the function generator. It didn't make any difference. You know, I could say 3 volts peak to peak, and all that means is I could adjust my pot for anywhere from 3 volts peak to peak down to 0. And of course, 10 millivolts, which is here. So here's VN. Now this is VCC, and people get that confused. They think VCC is VN, but VCC is the power supply, right? VN is what we're trying to amplify, and then this right here, we call this V out. And we calculated this to be, what do we measure this to be? We measured this to be 1.7. What do we measure this? Back on that table that we just looked at. 1.7 something, right? 1.73 or 1.7. And then we measured this. What did we measure? So we measured VB to be 1.73 volts. We measured RE to be 1.0 what? 05. And then we IE, we came up with IE was what? 477 microamps. And then we calculated VRC. We have to calculate VRC to get VC. We calculated VRC to be what? 6 point what? 8 volts. So voltage collector to emitter would be equal to 10 volts minus 6.8 volts. So what should that give me? We got something wrong, huh? 3.2. Where did we come up with 5 point something that long ago? So my voltage to collector to emitter is 5.6 volts. So what do we got wrong? So 477 times 10 to the minus 6 times 6,800 equals 3.2. So this is where we got, this is VRC. Y'all gave me, so VRC, which is not in the table, but you got to calculate VRC to calculate VCE. I calculated 3 point, about 3.3 volts. And so that's what we did. Somehow we, so VC is going to be equal to 10 volts minus 3.3 volts, which gives us, what? A 5.7 or whatever we got last time. Are we okay? So I don't know where the 6.8 came from. So this indicates we're in the active region, right? Oh, I'm sorry. I can't do math. And that's where y'all was trying to give me that right there. But we have to calculate the voltage drop across RC to come up with VC. So let's do VC. So VC, not, so let me redo this. So I did that wrong. So VC would be equal to 10 minus 3.3, which is equal to 6.7. Voltage collector to emitter is going to be voltage on the collector, which is 6.7, minus voltage on the emitter, which is 1.05 or 1.1. You code? Oh, I thought I didn't see your arm. I'm sorry. So 1 point. Oh, okay, that's fine. Let's use 1.1. We'll just round these. So that means it's going to be around 5.5 volts, right? Well, I don't see my camera. Oh, I didn't open it up as well. Oh, no, it was paused, guys. So I'm going to redo this so it get recorded. So what we're trying to do is we're trying to calculate the gain. So we got two formulas we could use. We could use R out over RE prime if the emitter resistor is bypassed. So that's the one we're going to use. And then we would use R out over RE if it's not bypassed. And then what we're doing now is trying to calculate R out. So our output is generated right here. So this is representing the source of our signal right there. So there's our transistor. And then that would be that point right there. And what we see is we have this is in parallel with that. Now what we're doing is we're ignoring the capacitor. And why are we ignoring the capacitor? Because if we choose it, and we're not going to get into how you choose it, you'll learn that in AC. But we will choose it so it'll have almost no opposition at the frequency that we're operating at. So what we end up with is we end up with my collector resistor in parallel with my load resistor. So this is the equivalent circuit right here. And what we're doing now is calculating what R out would be. So what do y'all come up with R out? Of course, we're rounded to 1 decimal point after we get the engineer notation. So what's R out? Didn't take that long, guys. I did it on my calculator. What we got? I know it's going to be less than 6.8K, right? You understand? So what we got? Everybody, y'all scared to give me the answer? So what we got? No. What'd you say? Yeah, but we'll say 4.1K. So the formula would be 1 over 6.8K plus 1 over 10K. That's the formula. Or you can use what we call the product over the sum. But what's nice about the reciprocal is you can do that without using parentheses. And somebody might have told y'all, well, when are we going to ever use this again? By the way, Miss Shawanda Thomas teaches the Honors College mathematics course. And she was amazed at our formulas, showing them to her class. Because she says that's when she's got the biggest problem. People don't see a use for the math. Why do you need to learn this? And a lot of people in DC, they'll get through DC and they forget everything. I passed DC, I don't need to know this. And then you get into solid state and you say, well, almost everything that we do in this class, all we're doing is applying stuff that you learned in where? In DC. So 6.8 times 10 to the third, then I'd hit the reciprocal key. Then I'd say plus 10 times 10 to the third. Then I'm with the reciprocal key. Then I got to hit equals, right? Y'all understand? To make it do all that math. And then I take the reciprocal again. So we're going to use 4.1K. Are we okay? Now what's RE prime? What's the formula for RE prime? Yeah, so RE prime is equal to 25 millivolts over IE. Now what was our IE? 400 and what? 477 micro. And I've got a little delay in my computer between what I'm writing and what's appearing. So what are we expecting for our RE prime? What's RE prime? It's around what? 52.4 ohms. Ohms, Rich. I got okay, so now we can calculate what our anticipated gain is. So my anticipated gain, AV, would be equal to 4.1K divided by 52.4. So what's my calculated gain? About 78.3. Or it's about, here when you deal with fractions, it's basically worth a waste of your time. So it's going to be a gain of about 78. Now, I'm going to put this big approximation right here because this is a definitely approximation. So RE prime is an approximation. Right, you understand? This is an approximation, right? You understand? Because if we wanted to get this precisely, then we would have to somehow measure RE prime. And we could do that, but it'd be very complicated. And what you're going to find out is just not going to make that much difference. So basically anything between 50, probably any gain between 50 and 90 would probably be considered to be within the range of this approximation. So what I have, I don't know why I lost my full screen. Oh, I know I did. So here's my circuit. And you can see, we could spread it out. I guess I should have, but it made it a little easier to see. But here's my transistor. This is a 2N3904. It's an NPN transistor. It's got a typical beta of around 100. Here's my 6.8K. It goes up to power. Here's my 4.7K, 47K, excuse me. It goes up to 10 volts. There's 10 volts right here. Here's my output resistor. It's 1/8 of a watt. It's a little old tiny thing. Here's my input capacitor right here, and I've got the negative pointed back toward the signal source. Here's my output capacitor, and here's my 100 microfarad bypass capacitor. I got my channel 1. Here's channel 1. It's hooked up to the input. Here's my input. This is coming in from my 10K pot. And here's channel 2 right here. It's hooked up on my output capacitor. So here's my output capacitor right here. And here's my oscilloscope. I don't know what happened, guys. Here's my oscilloscope. So the one on the top, I don't know if you can see this. I have this set on 5 millivolts per division. So we got 2 divisions, so that's 10 millivolts in. Here's my output. It's set on 200 millivolts per division. I'm going to put it so we can measure it. So I'm going to put it on the flat line. So this would be 200 millivolts. This would be 400 millivolts. Okay. So this would be 200 millivolts. This would be 400 millivolts. This would be 600 millivolts. This would be 640. This would be 680. This would be 720. Or let's do that. Make sure I got that right. So it's 123.243. 3.3. 3.3 times 200 millivolts, 640. Excuse me. Okay, is that right? That should supposed to be. Got it on 200. 1, 2, 4, 2, 4, 6. 6.6. So 6.6 times 200 millivolts is 6.6 times 200 millivolts is 1.3 volts. I'm sorry, 3.6. Rich. 3.6 times 200 is 720 millivolts. Is everybody okay? Did y'all get what I get? Yes or no? Are we okay? Even though I did get kind of confusing. So all we did, we got 2 ways. I counted, but what we're going to do is do it the math. So I'm counting 1, 2, 3. And each one of these are 0.2, 0.2, 4, 6. so it's 3.6 divisions times 0.2 volts. That's 720 millivolts. So I'm putting 200. So what's my gain? What's my measured gain? Now we calculated 78, but now we just measured it. So you have to understand this is a calculation. This actually was better than it was a while ago. So this gain right here is calculated. This is not measured. This is calculated. But I know gain. How do we calculate any gain? Dang it. Why do you keep doing that to me? So how do we calculate gain? Any gain. How do we calculate gain? What's gain? How do we calculate gain? What'd you say, Courtney? Yeah, but how would we calculate it? Or yeah, or any, but that's exactly right, because gain is always out over in. I mean, no matter what. So we're trying to do voltage gain. So what we did is we measured 720 millivolts out, and we're putting 10 millivolts in. So our AV is going to be this right here. So what's our AV? Our measured AV is 72. We computed what? 78. A while ago I got 68, so something's happened since then. That's okay. But see, that's really good because we used so much approximation. So we got a gain of 72. What's this unit right there? No unit. Gain has no unit. How many dB would this be? So I'm going to say 72. I'm going to hit the log on that, which gives me 1.85. And then I'm going to multiply that by 20 because this is a voltage measurement. So this is about a 37.2 dB gain. Which is not bad. So, what do we need to do now on the lab? So there's our gain. Let me find the lab. There we go. So this is the chart right here we're filling in. So our computed RV gain was 78. Our measured was 72, right? Our V out was what? 720 millivolts. Oh, what did we compute? So our computed would be our AV times our VN. So our computed AV was 70 in. So our computed V out would be equal to 10 millivolts times 78. So we computed we was going to have 780 millivolts. So that's what we computed. Everybody follow me? And what did we measure? We measured 720. So our measured gain was 72, and our measured output was 720. Anything else in the chart? Oh, RN. Okay. So we need to do RN. Or I usually call it ZN. It might be ZN in my data sheet because we're putting AC into the thing. Are we okay so far? Okay, so what I'm going to do is get rid of all the stuff I had to say for some reason, Mike. Okay, so here's Rn. So here comes my input signal. Now this is the one I should have kept. So here comes Rn. Now Rn sees a DC source as a ground. So my input signal is coming in here, splitting right here, splitting right there, and it's going through here, and then it's bypassing and going that direction. Now why don't it go that way? Why don't my signal go that way? Somebody got any reasons why it don't go that way? Because the base to collector is reverse bias. So we don't get any current flow between the emitter and the collector, but your base to emitter is forward biased, right? You understand? So this is what our input sees. So here's my signal. So it's going to come over here. We're going to ignore that capacitor. Now, eventually, later on, if we got into really detail, you can't ignore it. And then I'd come over here. The first thing I'm going to put is I'll have a 10K. And the next thing I have is I'm going to have a 47K. And the next thing I'm going to have is when I go through the transistor, is I'm going to have a 2.2K times the typical beta. What did I tell you the typical beta was? 100. So from the base, your emitter resistor is seen as times beta. So instead of using 2.2K, I'm going to use 220K. So my RN would be equal to 1 over 10K plus 1 over 47K plus 1 over 220K. And that's why we ignore that emitter resistor, because it's seen as such a big resistor. Pretty close to AK. Look at AK. So the trick that they use to measure ZN is pretty interesting. So if I come over here and I have two resistors, and this right here is a pot, and this right here I don't have any idea what it is. All I know is this is 10 volts. Now when I adjust this, and this point right here gets to 5 volts, what do I know about those two resistors? What do I know about those two resistors? Huh? Okay, but I'm talking about the ohm value. What do I know about the ohm value of those two resistors? Well, they're dropping the same voltage. They're in series. They've got the same current. If they got the same current, they're dropping the same voltage. What does that tell me about the R value of those two resistors? They're the same. They got to be the same. Now, the problem is this right here is an AC resistance. This is a dynamic resistance. This right here is not. This is going to be a fixed resistor. I'm not a fixed. It's going to be a variable resistor. It's going to be a pot. So what we're going to do is we're going to get a nice output over here. And what we're going to do is we're going to come over here and we're going to put a pot right here. But we're going to wire it to act like a rheostat. And what I'm going to do is I'm going to set it to 0 ohms. And then I'm going to measure this output. Let's say it's 5 volts. And then I'm going to start dropping this until it drops down to 2.5 volts. So what that tells me is the input impedance of the amplifier and that pot have to be equal to each other, or that rheostat have to be equal to each other. So what I can do now is I can measure the rheostat, and whatever the rheostat gives me, that's the input impedance of the amplifier. Does that make sense? We could have it anywhere. Yeah, well, I think it says it goes right there. Thing. Either way would be fine, because as long as I get it before this resistor right here, we're fine. So what I'm going to do is I'm going to take a pot. Where's my pot? Okay. And that would be easier to put it right there anyway. Or you suggested. So here's my pot. So here's my pot that I'm just at my 10 millivolts at. And I'm just going to take this pot, and then we'll have to do a little moving around a little bit so I can get 2 slots. Here's where my input signal is coming in, right here. What I'm going to do is I'm going to move this over a slot. I'm going to come over here and so we turned it into a rheostat by putting two together, and then I'm going to insert this back into my input. We got a bunch of stuff in there, guys. We're adding a bunch of noise into it. What happened to my output? Oh, my scope of it came disconnected. No, there it is. Okay. I touched two of these together. So we're not really concerned with our input anymore. So here's my output. We're going to have to adjust it so it don't. I'm sorry. Let me change my trigger over to channel 2. see channel 2 in there. And what I'm going to do is I'm going to adjust this one so we get maximum gain. So now we got 0. We got 0 there. And then we'll adjust this one so we get a good signal that we can measure. Okay, so that's 500 millivolts per division. So that's 1, 2, 3, 4, 5 divisions. So what would that be? Huh? 500 millivolts. 5 divisions, that's 2.5 volts, right? Let's adjust it so we can get it a little easier. 2.5, let's adjust it down till we get 4 volts. Okay, so let's 4 volts. Because what we're going to do now is we're going to start adjusting this until it drops down to, what's 1/2 of 4? So that's 4 volts. We're going to adjust this input, we're going to adjust this resistor till it drops us down to 1/2. So as soon as my output drops down to 1/2, because the gain is fixed, right? We're not going to try to do this on the input because we'd be dealing with 10 millivolts on the input. But the gain is fixed at 77. Okay, right? You understand that? So what I'm doing is I'm looking at the output where I've got that gain. So now instead of trying to deal with 200 millivolts, I'm dealing with 4 volts. But when I adjust that series resistor right there, see, every time I come back, it's exiting me out of that. So what we have is we have this. And now I'm no longer concerned by input voltage. So what I've done is I've adjusted this till I got 4 volts peak to peak right there. And I know the gain. So what I'm going to do is I have my rheostat, my pot wired as a rheostat right there. So right now I have this set to 0 ohms. Now what I'm going to do is I'm going to adjust this to this voltage drops down to 1/2. So it's setting it about 1.7 volts. Well, I'm sorry. We're putting 10 millivolts in here, not this. Well, the problem is I'd have to adjust that from 10 millivolts down to 5 millivolts, right? You understand? Not using this pot, using this one. But this guy here's, we got a gain. So instead of me trying to deal with millivolts over on the left-hand side, then I'm going to deal with volts over on the right-hand side. So what I'm going to do is I'm going to start adjusting this rheostat, or this pot wired as a rheostat. I'm going to start going up until this guy drops down to 1/2. So it's going to drop down to what? 2 volts. As soon as I do that, I know that the value of that equals to the value of that. So right now I have 4 volts. And then what I'm going to do, I can't measure the impedance of the amplifier because it's dynamic. I'd have to turn it off. Well, if I turn it off, then I'll lose the transistor. Transistor's not even in the play anymore, right? You understand? I can't put my ohm meter into a circuit with power applied. But what I can do is I can adjust this till this drops down to 1/2. When that drops down to 1/2, I know that rheostat equals to the input impedance of the amplifier. Then what can I do? Well, I can turn it off and I can measure the value of my rheostat. So the value of my rheostat is going to equal to the input impedance of the amplifier, right? Everybody understand that? You with us back here, Courtney? You sure are quiet. So here we go. We're going to start turning this guy down so it drops down to 2 volts. So here it comes. You can see it starts dropping down. And we're going to drop it down to 2 volts. Right there. Of course, this don't have to be perfect, but that's pretty good. So that's 2 volts. Okay. Everybody understand this so far? So I don't need to take this off. I need to set it there. So what I'm going to do now is I'm going to come over here and I'm going to disconnect 1 lead of my pot, turn the power off. Not the pot that's setting the input voltage, the pot that's doing the input impedance. So I'm going to come over here and I'm going to take this thing and I'm going to take out 1 lead right here. And then I'm going to take my meter and I'm going to put it on ohms. Put it on 20K because we know it's about 7K. And then I'm going to come up here and I'm going to measure the value of this pot. And it's measuring 4.4K. So that's the approximation. This is actually what it is. We calculated what did we calculate? 6 point, no, I'm sorry. What did we calculate? Huh? RN. AK. And it's measuring almost half of that. So 4.4K is the measured value of RN. I know what's happening when I hit this. Is it that? That's also exiting me out of my power. So this is what we did right here. They put it on the other side, but it don't make it, y'all understand, it don't make any difference if I put it right here or put it right there, because we're halving the input signal anyway. Now we're going to do some troubleshooting. We already did that. It says, restore the circuit in figure 34 with a 2-channel oscilloscope. Compare the input-output waveform. What is the phase relationship? Okay. So let's turn it back on. I'm gonna hook my pot back up. I'm not gonna take it back out. And I'm gonna adjust it back up. And then I'm gonna bring up channel 1 again. And we know what's the relationship between the input-output phase of a common emitter amplifier. They're either in phase or they're out of phase. So what's the phase relationship between the input and output of a common emitter amplifier? So when my input signal comes in, now we're taking our output across the transistor. So when the transistor turns on, its resistance goes down and the output voltage would go down, right? You understand that? So when this input signal goes positive, that's going to cause this to go positive. It's an NPN transistor. It's going to turn the thing on. So that means the output is going to start going negative. And then when the input goes negative, the transistor is going to cut off and the output starts to go positive. Now it doesn't ever go positive. You have to understand, guys, that right there is not AC. That's DC changing at an AC rate. Transistor amplifiers are DC amplifiers. But we can make it appear to amplify AC by using what? By using capacitors. So the capacitors will let us put AC into a DC system and subtract from the base voltage, right? You understand that? And allow us to generate DC at that collector right there. So if we looked at the collector, what we'd see, this would be 0 volts, and the signal is going to be doing this. It's riding on DC. And of course, it's got to be between 0, if it saturates, and up here, when it cut off, this would go to 10 volts. So if I input too much voltage, we're either going to clip the bottom or we're going to clip the top, right? You understand? So we're biased at, what's our VC equal to? 6.8 volts. So we're biased toward cutoff. We would like that. If this was biased perfect, VC would be equal to 5 volts. That way you could go 5 volts up and 5 volts down. But you're probably never going to see that because we're going to use standard resistors. Right? You understand that? Now, I was telling y'all we could bias this thing right in the center if we came in. I think Brian asked that question. Couldn't we do it if we put a bunch of resistors in series and stuff like that? And that's true. We could do it. But what you're doing is you're adding a lot of cost to something that you can get by with, right? You understand? As long as you know where it saturates and you know the maximum input signal that you could put on this thing. If you know the maximum input signal, you would never put more than that on there. And then what you do is you run it through multiple stages, right? You understand, to get the gains that you want. So if I come over here and look at this oscilloscope, and I come up here and start changing my input signal, so I'm going to start increasing my input signal. My blue is the output. Oops, wrong thing. You see now it's already started to store. You can see it should have clipped on the bottom first. Looks like it's clipping on the top first. Bias toward cutoff. But as long as we stay below a certain input voltage, then we get a nice waveform out, right? You understand? So all we have to do is understand the limitations of our amplifier. Look at the phase relationship between my input and my output. Let me put it back where I'm not clipping my so we're triggering on this. So what's the phase relationship? So when this one's negative, when this one's maximum negative, this is maximum positive. When this is maximum positive, this is maximum negative. So it's 180 degrees out of phase. Common emitter, they're 180 degrees out of phase. Common collector, they're in phase. Now, what difference would this make to the human ear? Huh? Nothing. Because your ear don't hear phase. All you hears is amplitude and frequency. So as long as you don't get your left and right channel out of phase with each other, then you got no problem, right? You understand? But as long as you have the same phase shifts all the way through your left and right channel, so this is why your channels are all identical to each other. So common emitter, 180 degrees out of phase. So what's going to happen when I remove C2? What should we anticipate to happen? So here's C2 right here. So what's going to happen when I remove C2? Well, we got two gain formulas. No, it's going to be biased because it don't bias through the capacitor. It don't bias through the capacitor, it biases through the resistor. Sorry. Let me go back to my PowerPoint. I just went right past it. And we did it the other night. That's what we did right off the bat is we deliberately did not bypass. So our two formulas for gain, we have two formulas for gain, depending on RE, whether it's bypassed or not bypassed. So what we're going to do is right a while ago, we said, okay, we got one gain. So our gain, AV, we got two formulas. We got R out over RE prime. This is bypass. Or we got R out over RE. So what was our R out? What was our R out? What was our R out? You gave me the answer, but what was our R out? Okay, so we said 4.1K over 55 ohms. Okay. We said what? Yeah, I know. I'm sorry. So I got 4.1K over 52 ohms. And what did that give us? Okay. And let me get my formulas right. And of course, we calculated what? Calculated with what? 78. Okay, so here, AC has got to flow through that resistor right there. So before IE was bypassing that resistor, my AC signal was bypassing that resistor. Now it's got to go through that resistor. So now my gain is going to be equal to 1.4K over 2.2K. So my gain is going to drop down drastically, right? You understand that? Now my input impedance goes up, right? You understand that? What's that? So we calculate our input impedance wrong over there. Let's redo our input impedance. So it was my fault. Because we were really, really off. I should have said something's got to be wrong. So that was my fault. So this is 10K. This is 47. It ought to make y'all feel good when I make mistakes. Right? And this is going to be beta. This is bypassed. So this is beta times RE prime. So this is going to be equal to 100, or typical beta, times 55. Now this is going to work out better. Sorry, guys. This is going to be 55K. So Rn bypassed would be equal to 1 over 1 over 10K plus 1 over 47K plus 1 over 55K. So a while ago we calculated it to be what? When I used 220K over here, what did we calculate to be? 7.8K or something? Huh? 8. Yeah, 8K. And we measured 4.4K, right? So that's 10K reciprocal plus 47K reciprocal plus 55K reciprocal equals reciprocal. Yeah, this is wrong too. Sorry. This is 5.5K. I can't do math. Slow down, Rich. So it's 10K reciprocal plus 47K reciprocal plus 5.5K reciprocal equal reciprocal. There we go. So this comes up to 4.9K. And what did we measure? We measured what? 4.4. That makes a lot better sense. This is 5.5K, guys. It's not 55K. I looked at that and I said, that can't be 55K. So look what happens when we bypass it. REN basically doubles, or we lose all that gain. When we bypass it, REN halves, but we get a bunch of gain. So here my gain would be what? 4.1 What's that? Divided by 2.2K. You can drop the K, so it's 1.9. So look what happened to the gain. So bypassing, we got a gain of 78, but you don't get anything for nothing, right? You understand? If I lower my input impedance, that means my signal source is going to have to provide more current. If I lower my input, if I raise my input impedance, it means my input signal has got to provide less current. But here, to lower it, the only thing I can do is take out that bypass capacitor, and we go from a gain of 78 to a gain of 2. But now I've got a gain of 2. And I've got a current amplifier now, right? You understand? This guy amplifies current. So I could take this gain of 2 and my next amplifier might be bypassed. Y'all understand? So when I come over and hook this up to my signal source is going to always have it's going to have an impedance. So it's going to have an impedance or a resistance to it, right? You understand? And if we put current through a resistance, we drop. So what I would like to do is I would like to match a high output impedance to a high input impedance. And a common emitter just don't do that unless we do what? Unless we deliberately swap it is what they call it. You deliberately reduce the gain. So what's going to happen if something happens to this capacitor right there, then my gain is going to go way down. I'm still going to get gain, but it's going to go way down. And that's basically what we're trying to do, is going to try to figure out what's going to happen when different things go bad. So if this capacitor, my gain is going to drop way down. What's going to happen if R1 opens? Resistors open all the time, guys. I mean, they don't. So if C2 opens, then our gain goes from 78 or 70, whatever it is, down to 2, right? So what's going to happen if R1 opens? So what would my VB go to? VB would go to what? 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 So, 0, good. VB would go to 0. Right? So, of course, R2, if I measure across here, this is going to equal to 10 volts because this is series. It's a series circuit, right? You understand that? VB would go to 0. What would happen to my output signal? Is it going to increase or decrease? It's going to what? How's it going to increase? We haven't. Okay, good. I'm sorry. I just heard you. It's going to go way down. But what's going to happen? My input's 1 volt, so it's going to exceed 7/10 of a volt. Now, transistor's going to turn on, but it's going to give me these little things like this up there. So we're going to lose the whole positive alternation on the output, and we'll get the this voltage right here is going to go to, what's it going to go to? It's going to go to 0 when I measure it with my meter, right? You understand? This right here is going to go, transistor is going to move toward cutoff, but it's going to have, this guy here is going to go way up. So let's see, first of all, let's open the capacitor and see what's happening. So let me bring my scope back up. And I'll give you all a break after we do this, and we'll start the troubleshooting. Okay, so what we're going to have, my input's right here. This is my output. Here's my bypass capacitor. I'm going to open it up. It looks like my output went to 0, but my scope is just turned up. Let's turn it up. So it's still there. But now, that's the difference. So I'm putting 3 volts in, 1, 2, 3, I'm putting 30 millivolts in and get 10, 20, 30, 40, 50 millivolts, a little over 50 millivolts out, which is a little over a gain of 1, right? You'll see that? Put the capacitor in. And it shoots up like that. Okay. So that's one problem. So what happened to the gain? Well, the gain went from 70 something down to 1 point something, right? About 2. So if you're in an amplifier and you're getting out nowhere near the gain that you expected, then that would be one of the problems you anticipate. Okay, guys, y'all go ahead and take a break. So we compared the input, we removed C2, and then we're supposed to look at our bias voltages again. So why do you, if I open C2, what effect would you think that would have on the bias voltage? If I open C2. So what effect would opening C2 have on the bias voltage? It has a lot to do with the gain, but the bias voltages, that 1.7 volts right there, right? That 1 volt right there, that whatever that was supposed to be right there, what effect would that have on what opening C2? What effect would it have on the bias? So Randy says she thinks it's going to increase the emitter bias. What sets the emitter bias? Well, the emitter bias is set by that voltage right there. It has nothing to do with that dang capacitor. All that capacitor does is change the gain. When we calculate these voltages back in your worksheet, when we calculate those voltages, we didn't even have a capacitor there. So what would it do to our bias voltage? It's not going to do a dang thing. They're going to stay exactly the same. Right? You understand that? Well, what's nice about AC gain is going to go down, but I'm going to put an AC signal on this. But my DC is going to not be affected by the AC signal. And why? Because my AC signal is doing this, and of course we're putting AC on there. So my AC signal is doing this. So what we've got is we got this setting at 1.7 volts right here. And here's my transistor. And we got this setting at 1.7 volts. And what my AC signal is coming through this capacitor, it's varying that 1.7 volt. So it's either going to add to it or subtract from it. But what's my meter going to do? My meter's going to average that right down the center. And it's going to show me 1.7 volts. Well, if I got an AC signal. So what's so nice is that you can measure the bias voltage even if there's a signal coming in, as long as it don't saturate or cut off the transistor. If you cut off the transistor, it's going to throw your bias all out of whack, right? You understand? So I've still got an AC signal coming into this thing. Here's my scope, and it's right now it's not bypass, but it don't make any difference. So there's my scope. So I've got an AC signal coming in. I'm getting an AC signal coming out. So I'm going to come back and measure my bias voltage. So I'm going to swing this back over on my meter. I'm going to put my meter back on PC. Right here somewhere, Rich. There we go. 20 volts ought to be okay. And I'm going to hook up my hook my black lead back up to my common or my ground. And I'm going to measure my base voltage. So here's my base voltage. It's still setting at what? Still setting at 1.7 volts, right? Here's my emitter voltage. Oops. Here's my emitter voltage. It's still setting at 1 volt. Here's my collector voltage. What's that resistor at? That resistor is right here. It's still setting at 6.6. So say even though that capacitor's open, it has nothing. Here's it. I'm disconnected something. Yeah. Oh, I know what it is. So now I've got it. So this is bypass. Then we come up here and measure this, and it still measures the same. So that bypass capacitor has nothing to do with the bias. Y'all understand that? So what's the next thing it wants to do? What's the lab wants to do next? So we're going to move what resistor? Okay, so I've got it back in there. R the load. So what's going to happen when we move R the load? Huh? Alpha's definitely going to change, but is it going to go up or go down? We're going to get more gain or less gain? A while ago, we know that gain, So AV, and we got it bypassed, so AV would be equal to R out over RE prime. So you're right, the gain is going to change. Bias is not going to change, but the gain is going to change. Because the gain is set by R out over RE prime, or is set by R out over RE, depending on whether this is bypass or not, right? Okay. Well, what we're changing is we're changing R out. If we change R out, we change the gain. So a while ago, we looked at our out circuit. We said, okay, this is our transistor. And then right now we're looking at 6.8K in parallel with 10K. And we calculated R out to be equal to, to 4 point, what did we calculate it to be? What's that? 4.1K. Well, what happens when that opens up right there? What's R out going to be equal to now? It's just a simple circuit, guys. It's just a simple resistor. So what's R out going to be equal to now? 6.8K. So a while ago, we said, okay, AV is going to be equal to 4.1K over 55 ohms. Now we're going to say AV is equal to 6.8K over 55 ohms. So what's the gain going to do? The gain's going to go up. But it's not going to do me any good because I don't have an amplifier that don't run a load, right? You understand that? But load's open. Well, what we're going to see is this is the way when I'm troubleshooting, I'm expecting a gain of 70 something, and all of a sudden I'm getting a gain of 90 or 100, and I say, well, something's got to be going on. This amplifier is not loaded. So when we load an amplifier, the output goes down, right? You understand? If we unload it, the output goes up. And we talked about that. So I could go get a battery out of that shelf in there, and I could put a voltmeter across it, and it's going to measure a voltage. I put a resistor across it, and the voltage goes down because we're loading it, right? You understand that? And we don't have anything in there to compensate for the load. So the gain is going to go way up. So I'm going to open up the load. So I'm going to flip back over to my scope and put it so we can see what's going on. I'm not going to make it full screen. So here's channel 2. So right now we're getting this voltage out right there. Okay. And I'm going to come up here and I'm going to remove the load. So here's my load right here. So my load opens. How'd the gain get? Shot way up, right? I see that. Make sure I get to the right place. Okay. Here's the load in there. So right now we're getting a gain. We're putting in, this is 50 millivolts coming in. We don't need to maintain the 10 millivolts anymore. And I'm not bypassed. Sorry guys. Bypass. I've lost my bypass. Okay, there we go. And we need to lower input. You can see my output starting to, there we go. Okay, so roughly we're putting 5 millivolts per division, 50 millivolts per division. We're putting a little less than 50 millivolts in. So I'm putting 50 millivolts in. And it's already starting to store some, and I'm getting 1, 2, 3 volts out. And I'm going to come up here now and I'm going to open up the load. And what did the gain do? So the gain went way up, right? Understand that? Are we okay? So that says, okay, if this amplifier is doing what it's supposed to do, it's just that it's the load that we've got the problem with. If I measure the bias voltage, what's going to happen? They're going to measure the same, right? You understand? Because we hadn't affected the bias voltage. So does that answer that question? What are we supposed to do on there? Let me bring the lab back up. Replace C2, open it, and measure the AC signal voltage at the transistor's base, emitter, and collector. Measure the voltage gain of the amplifier. So let's measure the voltage gain. So we're putting 50 millivolts in. I've got one division. That's not exactly accurate. Let's make it a little more accurate. So I'm putting 50 millivolts in. I'm putting 40 millivolts in. And I'm getting 1, 2, 3, 4, 5 volts out. Let me adjust this down somewhere. Okay, so I've got it on 20 millivolts per division in. I've got it on 500 millivolts per division out. The top is my in, bottom one is my out. So what's my gain? Straight. Now see that? What's the gain? The load is open. So I've got 1, 2, 3, 4.4 divisions on my output. Huh? 1, 2, 3, 4.24. Okay. So 4.4 divisions, 500 millivolts per division. .2 volts in. 40 millivolts in. No, 20 millivolts in. 2 millivolts per division. I got two divisions. 20 millivolts in and 2 volts out. 2.2 volts out. 2.2. What's the gain? What gain y'all got? We're expecting a gain of around 70. We're getting a gain of what y'all got? So come on, give me an answer. What we got? What's the gain? So out divided by in. 20 millivolts in, 4.4 volts out. What's the gain? So the top is my input. I have it on 10 millivolts per division. I have it on 10 millivolts per division. I got two divisions. That's 20 millivolts in. I got my channel 2, which is the blue one, on 500 millivolts per division, or half a volt per division, right? So that's 1, 2, 3, 4.4 divisions. It's 2.2. Right? Everybody okay? Yes or no? Did I say that right a while ago? So what's the gain? No, gain has no unit. Gain has no unit. Y'all understand that? We can do it in dB, but dB is like using engineer notation. So dB is not a unit, right? You understand? It's just a way we can represent large numbers and short numbers with very few characters. So I've got 2.2 volts out. I'm bringing in what? 20 millivolts in. What are you saying, Courtney? It's got to be better. It's got to be bigger than 77, right? So what we got? Yeah. So now we're getting a gain of 110. So we're getting 30 over what we thought we was going to get. 110 would be equal to log times 20. It's going to equal to 41 dB. Okay, so what's the next thing we're supposed to do? So we measured the input. What's the input? That's what it says. Measure the input voltage, what we got on the base. We got 20 millivolts on the base. What do we got on the collector? AC on the collector. We got 2.2 volts on the collector, right? You understand? Which gives us a gain of 110. Are you okay? There's my lab right there. And we open R2. So what's going to happen when we open R2? We already talked about that. What's going to happen when we're going to open R2? No, we haven't. What's going to happen when I open R2? So what's going to, when I open R1, the gain is going to go down, right? Because it's going to go to almost zero. What's going to happen if I open R2? So what's going to happen to my base voltage? Is it going to go up or is it going to go down? Yeah, it's going to go up. You're right, because we've lost that bottom voltage divider, right? You understand? So we've lost that bottom resistor. Those two resistors in combination are setting that. So what's going to set the bias now? We ignored this over here because it's times beta. So if I was to come over here and put, a 10K in parallel with so let's say this is a 10K. This guy's seen as times beta, so it's seen as 220K. What would be that total resistance right there? What would be RT? Well, if I take 10K, and I'm going to take the reciprocal of that, and I'm going to add that to 220K, I'm going to take the reciprocal of that, and it comes up and gives me 9.6K. So what we're saying about is if this thing's times beta, we ignore it when we calculate that voltage divider because it's so big, right? You understand? Now what happens is now this resistor right here is setting that voltage right there. So what we have now is we have basically we have a 47K and we have a 220K. So my base voltage is going to go way up. If my base voltage goes up, the transistor moves towards saturation, so the transistor is going to saturate. This is K up here, Rich. So let's see what happens. So I'm going to come over here. I'm going to put the load back in. Try to put the load back in. Make sure nothing's touching. And I'm going to open R2. And the output's going to be really distorted. My bias voltage is going to be all out of whack, right? You understand? I'm going to open up R2. I need a pair of Nemo pliers because it's down here. So R2 is open. My output went to 0 because the transistor is flat saturated. It's probably not 0. It's just that we don't have it turned down long enough. What you'll find out, guys, is AC gets through anything. So it's still there, but it's almost nothing, right? That's 10 millivolts, 10 millivolts. Let's come in, let's measure our bias voltage. I'm going to come over here. I'm going to look at my base voltage. Instead of being 1 volt, it's up to 2.7 volts. Instead of being 1.7, it's up to 2.7. See that? Which means my emitter voltage now is way up to over 2 volts, 2.6 volts. Transistor saturated, so it can't. So look, it's not even dropping 0.6 of a volt. Oops. Oops, wait a second. My fault. Yeah. And my collector voltage is sitting at, where's my collector voltage? Yeah, it's setting, instead of being 6 volts, it's down to 3.3 volts now. So if this resistor opens up, the transistor saturates, your base bias voltage goes up, your emitter bias voltage goes up. If this resistor right here opens, then the transistor cuts off, right? You understand? Because that's what sets the base voltage. So you'd have almost 10 volts dropped across the transistor. If that guy right there opens, we got some strange stuff which we won't get into. The base voltage goes way down low because it's so weird. And I think that's all the lab calls for, right? I started grading labs. I'm sorry that got around to grading some. Normally what I try to do is grade labs real early to see if y'all are having problems with following procedures. There's a couple of y'all that more than one didn't do the conclusion. These labs are worth these labs are worth 100 points. And I pretty much will give you credit. So if I come over there and your circuit is not working, what do? I help you get it working. So that means when we get down to these questions, these labs are worth 100 points apiece. These questions are worth 5 points apiece, and the conclusion's worth 5 points apiece. Some of y'all are not even writing a conclusion about the lab, and that's what this is. This is the conclusion about the lab. Not the last thing you did, it's conclusion about what the whole lab, what you learned in this whole lab, right? Understand? Only if it, I mean, I'll go back and look at the procedures that I gave y'all out, and I can go back and look at the thing. Yeah, no, you don't have to, Courtney, but if you don't, I mark off 5 points. But it's on the, we went over the procedures of the lab, right? So this is your conclusion of the lab. These lab questions, I got 2 people that didn't turn in any lab questions. 5 points apiece. -5, -5, -5. In the procedure, we say you don't have to do the further investigation, but you got to do the what? You got to do the lab questions. If you don't lose the lab questions, then you get 5 points apiece, because your circuits are basically given to you, because when I come back there and grade it, if they don't work, I help you get them going, right? You understand? So a larger percentage of the lab form, not keeping up with your time. You know, if you work and you don't keep up with your time, if you do piecework, you know, you don't keep up with your time, you don't get paid, right? You understand? Some of y'all are not doing time. Some of y'all are not doing conclusions. Some of y'all are not doing lab questions. And I don't know what's going on. When I started grading, I've only got 2 lab 31s that were turned in. And then I got 1, 2, 3, 4, 5. I got 6 lab 32s. So everybody turned those in. On handout labs 1, I got 1, 2, 3, 4, 5. I got 5 of those turned in, so somebody didn't do that. Lab 3, handout 3, I got 1, 2, 3, 4, 5, 6 of those. So everybody done that. And then testing bipolar transistors, I got 1, 2, 3, 4, 5 of those turned in. Somebody hadn't done those. We just finished up lab 34. Huh? So why y'all don't? So the only I got lab 31. I think Courtney and yeah. No, where's lab 31? So lab 31, Kareem and Courtney turned in lab 31. 31 is the diode characteristics. That's the one where we actually went in and we did the reverse bias in the room. Huh? There's nothing in the to be graded box. So we did 3 labs so far out of the lab book. We did 31, we did 32, and then the rest of them have been handout labs, right? So 31 was the diode characteristics. 32 was all the power, the unregulated power supplies. Then we did testing diodes, we did testing transistors, we did what else did we do? Huh? Zener diode. Then we did a Zener diode. Now these hadn't been documented yet, so what I'm going to do is let y'all get them back and finish answering. You need to make sure you do the what. Well, they've been graded, so I'm going to have to regrade them. You need to redo the what, the conclusions. You need to answer the questions, the ones I've marked wrong. how do you identify, how do you use an ohm meter to identify the cathode of a diode? We had two people said reverse bias the thing. That would be like me. How can I identify the cathode? I don't even know if it's good or bad. So how do we identify the cathode? You have to do two things. One way you measure overload, the other way you measure a junction, right? You understand? Y'all understand? We had two people say, well, you put the black lead on, they said you put the black lead on the anode, you put the red lead on the cathode, and you measure an overload, and that's where they left it. What does that tell me? That don't tell me nothing. How do you check a diode? You have to check it in how many directions? You have to check it in both directions, right? You understand? You have to if you put the black lead on the cathode and the red lead on the anode, on the cathode, then it's going to measure, for a silicon, it's going to measure about 7/10. For germanium, it's going to measure about 3/10, right? If you put it backwards, it's going to measure an overload. So you just can't put the meter on there both ways to check a diode. You got to do what? So we had two people in the class says you put the black lead on the anode, you put the red lead on the cathode, the meter measures overload, and they just stopped right there. Well, if I hold two things in the air, it's going to measure what? It's going to measure overload. It's not going to identify a cathode. This could be anything. The thing could actually be bad. We had two people answer that. They said the advantage of a full wave rectifier over a half wave rectifier, they said the pulse frequency is 120 hertz on one of and 60 hertz on the other. What in the world is that advantage? When I'm looking for a power supply, what am I trying to get? What am I trying to get? I'm trying to get volts, right? You understand? So for the same secondary voltage, a full wave will give you twice the voltage as a half wave. Y'all understand that? So we had two people said, what's the advantage of a full wave over a half wave? They said, well, a half wave gives us 60 pulses per second, and so what would that have to do with a DC motor? A DC motor don't see 60 pulses per second. A DC motor don't see 120 pulses per second. It sees so much voltage, right? You understand? So what's the advantage of a full wave over a half wave? What's the advantage of a full wave over a half wave? For the same secondary voltage, the full wave gives you twice the number of volts than a half wave does. What advantage does a half wave have over a full wave? Yeah, it costs a lot less. So if I can get by with a half wave, I'm going to use a half wave. If I can't get by with a half wave, then I'm going to use a what? A full wave. But half waves are cheaper. They're cheaper to build. One diode, one transformer, one diode, you got it bad, right? If I go to a full wave center tap, then I have to have a center tap transformer, and I got to have two diodes. With a full wave bridge, I don't have to have a center tap transformer, but now I got to use what? 4 diodes. Well, we get double the voltage out. And of course, it always boils down to what? Money. So when I filter it, a full wave, since the pulses are occurring faster, it takes a smaller capacitor to get the output voltage. So half wave, we have to use a bigger capacitor because it has to run the load longer. So a full wave unfiltered, that's the cheapest you can get. Then when you start adding capacitors, then it's going to say, okay, what do I need, right? How much money am I willing to spend? How good of voltage do I need? But I had more than one person answer the ripple frequency when normally loads don't see the ripple frequency, they see the watt out of the power supply. So this thing right here says nothing about input frequency, it says nothing about output frequency. It gives me an input voltage and gives me a watt. It gives me an output voltage at a current. Right? Now how did it get that? Is it full wave, half wave? You don't know. In fact, this is a switching power supply. I'm going to give these back to you. And of course, I'm not going to give the handout labs because there was no questions on the handout labs. Okay. There was absolutely no questions on those. But so 41, do y'all have that in y'all's book? In y'all's lab book? Y'all look and see. But I don't know why we've only got 2 31s, excuse me. 2 31s turned in. We're not going to do this in class. How many of y'all went out and looked at the test review?